All right, so let us continue our lecture today. So last time we was discussing that we have, to show this equation, right? So let me explain again. So let me start with the following very simple things. So now if I give you a function f x which is 1, right? And I ask you, I ask you to find a function u such that u prime of x is equal to 1, right? And then you put a boundary condition, right? So so suppose that I ask you to find a function u such that u prime of x is equal to 1, which is f, right? Then you can tell me immediately that a u has to be a constant, right? Now, if I give you a function fx which is 1, and then I ask you to find a function u such that u second of x is equal to 1, which is fx, right? Then you tell me immediately that, okay, u prime of x has to be a constant, c 1, and then ux has to be c1x plus c2, right? So now what we were trying to solve is this equation, right? So I give you a function f, and this equation is too easy, right? So this equation is too easy, and I ask you I have the questions. I ask you to find a function u such that minus u second plus ux is equal to f, and this is satisfied only on a finite element 0, 1, and of course you have to introduce the boundary condition, right? Then you cannot find explicit solution, right? So in this case, this is an explicit solution and this is an explicit solution, right? So in this case, it is easy. U prime is equal to 1, solution should be a constant. This is an explicit solution. The second case is u second is equal to 1, so ux has to be c1x plus c2x, c2, and so in this case, you also have an explicit solution, right? So, but our case is harder, although it is not that hard, because it looks easier. It looks easy because you just add ux into this this u prime, right? But it turns out that this case is not that easy. So our question is that, okay, given u, can you find given f, can you find this u such that this equation is satisfied? So this is called an elliptic equation in one dimension. So basically, for this equation, we don't have an explicit solution. So basically, because for this you don't have an explicit solution. So this is kind of hard to find a solution for this equation. So then people people invented the so-called weak form. The second, how is the second derivative of first order polynomial is a constant? I don't understand. So your questions. So you are saying about this, right? So u second of x is 1. So u prime has to be c1x, right? Right. You're right. Right. Sorry. Right. Plus c1 Thank you. So thank you, Stephen, for pointing this out. Right. So C1x plus C2. You're right. So yes. So Stephen point out a mistake that I made. So U second is 1. So U prime has to be x plus C1, right? And Ux has to be x squared over 2 plus C1x plus C2, right? So this is an explicit solution, but our case is a little bit more complicated because you have to add a Ux here, and when you add a Ux here, the whole thing is destroyed. All right. So because we don't have an explicit solution, so then people introduce a so-called weak form. So if U is a solution minus U second plus U is equal to F, then it has to satisfy minus U second V, the interval from 0 to 1, plus interval from 0 to 1 of U V, and this is interval from 0 to 1 of FV, right? So if U is a solution of this guy, then it has to satisfy this equation for all V, because you just have to pick any V, you multiply that with this equation, you integrate, and then this is so if U is a solution of this equation, then it also has to satisfy this equation. So this is the strong form, and this is the weak form. All right, and then basically when you do the change of variable, you change it into U prime V prime plus the interval from 0 to 1 UV, and this is equal to in the interval of FV, right? So this is so we explained in the previous class that this is an integration by part, and then what we do is we apply the Lax-Milgram theorem. Lax-Milgram theorem. All right. So, and the Lax-Milgram theorem ensure that the weak solution exists, but it doesn't ensure that you have a solution for the strong form, right? So basically, because the strong form is complicated, people turn to study the weak form, and the Lax-Milgram theorem ensures that this weak form has a solution, not a strong form, right? So we show that this equation, the second equation, has a solution, not the original equation, right? But still, this is useful. Now, so from Lax-Milgram, so you have this from the Lax-Milgram theorem, you have that this equation has a unique solution. Right? So from the Lax-Milgram theorem, you know that this equation has a unique solution, but you don't know what is this solution, because so the solution view exists uniquely, but U doesn't have an exact form. Right? So this equation, you know that there is a solution by this complicated theory of Lax-Milgram and all of the LP space measure theory, everything. W1, 2, S01, all of those complicated space. By using all of those complicated functional analysis tools, you know that there is a solution to this equation, and this solution has to be unique. But we don't know what is the form of this equation, of this solution, right? Because the this guy is not explicit. All right. So then in order to find U, we need a special method. which is the so-called finite element method. Right. So in order to find this u, we need a special method, a finite element method, and we cannot solve u explicitly. We have to approximate u, right? So we approximate u by uh. All right. Right. So now, the idea is the following. First, so you have the space H, which is W012, and this is on 01, or this is also S01 on 01, right? Of course, so all of the finite element method we're gonna learn more in the class of finite element analysis, but at least in this last part of this class, I'm going to show you how you can use ideas from functional analysis to construct the basis for finite element method. So the point here is that, okay, you solve this equation 1 on this space, all right, and the space that you have is from 0 to 1. So we will approximate H, which is infinite dimension, by H small h. This is finite dimension. Right? So the key idea is that you approximate this infinite dimension space. This is a superlap space, but you have to approximate this superlap space, which is infinite dimension, by a finite dimension space. So the idea is the following. First, first you're gonna do the following. So you do you divide this 0 to 1 interval into we divide 0 to 1 interval into smaller interval, right? So you're gonna use so you're gonna put x0 to be this guy, x1 to be this guy, x2 to be this guy, x3 to be this guy, x4 to be this guy. Then you have x5, x7, x8, x9, x10. So here you have 10 interval, right? So then here you have 1 over 10, 2 over 10, 3 over 10, 4 over 10, 5 over 10, 6 over 10, 7 over 10. No, this is 8. So this is 9. This is 9, right? 8 over 9. All right. So basically, you're gonna divide this interval into smaller intervals. So you have the interval from 0 to 1, which is the domain that we try to solve this equation. All right. Then you divide that into 9 intervals, right? So this is from 0 to 9, 2 to 9, and 0 to 1 over 9, 1 over 9 to 2 over 9, 2 over 9 to 3 over 9, etc. All right. So this is how we do it. First, you suppose that x0 is 0. Then you suppose that this is smaller than x1, and this is smaller than x2, and this is smaller than xn plus 1, which is equal to 1. Right? Basically, here you're going to have n plus 1 interval. So we have n interval with length 1 over n, and I denote this to be h, right? So basically x I will be xi plus 1 will be I over n, and I plus 1 over n, right? So the point is that we divide the interval from 0 to 1 into n smaller interval, and each interval has a length 1 over n, which I denote by h. So this h is also the small h here, right? And then we so the n intervals will be able to form xi plus 1 to be I over n and I plus 1 over n, right? Any questions? Now we have to define. We now have to define h. So remember that h here is 1 over n, and we want h to go to 0, and meaning that we want n to go to 0, right? So how do we define this h? So the hs will be the following. The hs will be the space of all of the v which is in h. Vx, when you restrict Vx to xi plus 1, this will have the form of ci plus di, right? Which means that, and v, and then there's another condition, v is continuous on 0, 1, right? So we define this h small h space to be all of the function v in h. So this h will be h01, right? So this is h01, such that this v, when you restrict it, when you restrict this v onto about an interval like this, it will become a linear function, right? And v has to be continuous on 0, 1, right? So 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 v, when you restrict that onto this interval, meaning that v is linear on xi is plus 1. All right. So when you restrict v on this xi plus 1 interval, you have something of the form of the type cix plus di, right? So this is a linear function in which ci and di are constant, right? So they are constant. In other words, when you restrict all of the function in this h, you have a linear function on all of the smaller interval. So I have a questions for you. What is the value of v at 0? Right? Questions? What is the value of v at 0? Any suggestion? So what is the space H? Right, Stephen, we got it. So v at 0 has to be 0, and v at 1 has to be 0, according to Stephen. Yes, Tyler also got it, right? So why v at 0 and v at 1 are both 0? Because v belongs to H, right? Which is S0, 1, S0, and 1, right? So v belongs to this Hilbert space, which is the Sobolev space, H01. And what is the definition of S01? S01 will be all of the function v such that v at 0 and v at 1 are both 0, and the interval on 0 to 1 of v prime square dx is smaller than infinity, right? So because we choose v to be in H, which is S01, 0. So basically, v has to satisfy the condition that v at 0 and v at 1 are both 0, and this is satisfied. In other words, v at 0 and v at 1 are both 0. So so if you pick so this is x0, this is 0, this is 1, this is x1, x2, x3, x4, x5, x6, x7. So in this case, n is equal to 6, right? So in this case, n is equal to 6. So if you choose a function v, it has to be like this, right? Right? So this is a v in H 1/6, right? So this is a v in H 1/6. So in this case, S is equal to 1/6, meaning that n is equal to 6. N is equal to 6 means that you have 7 interval. What? 1, 2, 3, 4. Whatever. So the point here is that, okay, the point here is that, okay, 1/7, right? So the point here is that okay, you when v is in H1/7, then the interval so if you start with, so this function v has to start with 0 at 1 and 0, right? Because it has to satisfy the condition of H01. Then they have to be linear on each of the smaller interval. So basically you're gonna have a function like this, right? So basically this is the space H. So now our goal is to find a solution a solution U H such that UH belong to this space HS, and then you also have V of UH. V is equal to LU LV when V is in HS, right? So basically this is a subspace of H, and this is also a subspace of H. So the original equation is you have to find a U in H such that B UH is equal to LV for all of the V in H. So the original equation is that there is a unique U in H such that V is equal to LV for all of the V in H. Now you solve an easier problem, which is the following. You want to solve you want to find a UH which is of this form. This UH belongs to this subspace HH, which is a subspace of H. Why is it a subspace of H? Because we chose here V belong in the space of H. So basically here this is a subspace of H, right? So you choose all of the V in H such that when you restrict those V onto the intervals, those V become linear and those V has to be continuous. So this VH is a subspace of H. Now, our original equation that we show that we studied in the previous lecture is U in H. There is a unique U in H by Laxmingram such that BUV is equal to LV. And then this is true for all of the V in H. Now we solve something easier. We try to solve this equation. You have to find UH in this HS space, and this is a subspace of H, such that B of UH V is equal to LV part of V and H US, right? Any questions? So this is the finite. So this is this is the so-called variational formulation of the elliptic equation in the finite dimensional subspace. Subspace VH. All right, and the function UH is now the finite dimension, the finite element solution of the original equation 1. All right. So this is the original elliptic equation, right? And when you write it in this form, this is the variational formulation of this elliptic equation in the finite dimensional subspace HS. And the function UH here that you found is now the finite element solution of the original solution 1. So I'm keep telling you that this is a so we keep mentioning, we keep claiming that HS is finite dimensional, right? Why? So in this from the beginning of our lecture, I just keep claiming that VH is HH is the finite dimensional is a finite dimensional subspace of H. Why? So basically HS is finite dimensional space, since we can construct a basis, a finite basis for HS as follow. So who knows what is the basis for HS? Who knows? Right. So the basis for HH will be the following. So you choose phi, we choose phi I in VH, for I is 1 to n, right? And phi I of HJ will be 1 or 0. So if I is equal to J, and 0 if I is different from J, right? So no, Stephen said that. So you have a good idea. So Lagrange's basis functions is a good one, but so look. So the function that we have here is of the following form. So this is not Lagrange, and this is not delta, right? So those bases are not good. Why? Because suppose that on this mesh. So this is called mesh, right? So suppose this is a mesh, and the edge will be the mesh size. So what is our basis? Our basis will be those linear function. It has to be 0 at the two limit points, and it has to be as 0 at the two limit point, which means that it has to be 0 at 0 and 1. This is 1 point. Now on each of these interval, this is x0 and this is x1, this is x2, this is x3, this is x4, this is x5, this is x6, this is x7, right? We are on the, hi Jonathan, triangle is also good, but here we are on the line, so there's no triangle, right? We are in one dimension. So basically this is the basis. This is the basis. Let me explain to you why. Because all of the space VH, sorry, I keep calling it VH. So this is all of the function in VH has the following form. So it's going to be linear from x0 to x1. And because s0, it is 0. So it has to be like this, right? So now from x1 to x2, s has to be linear, right? Linear. This is also linear. From x2 to x3, no, spline is not good. Spline, again, spline is not good. Right, because you are seeing linear function, right? You cannot use Lagrange or spline, and delta function is not a smooth function. So this is also linear. This is also linear. This is also linear, right? This is also linear. So you see that this function is linear on each of the sub intervals, right? So which means that you don't have, so again, this function is, so what do we say? So we say that HS will be all of the V in S01 such that V is linear on xi is plus 1, right? So this is linear on xi is plus 1, and then it has to be continuous, right? So this is our definition. So which means that you have function like this. It has to be linear on each of the sub-interval, right? So now what is Lagrange? Lagrange will not be, Lagrange function will not belong to this space. Why? Because Lagrange is an infinite, so this is C infinity function. So here you don't have C infinity function, since Lagrange functions are C infinity, right? So this function is, look, this function is continuous, but it is not C1, right? So of course, if you look into this, V doesn't belong to C1. V belongs to C0, right? V is continuous, but it is not differentiable, because you see that there are points where they are not integrable, differentiable. So for instance, at x1 it is not differentiable, and x2 is not differentiable, and x3 is not differentiable. So this is a C0 function, and this is not a C1 function. So basically, Lagrange function do not belong to this space. This is first thing. So Lagrange is not good. Spline is not good. Spline functions are also C infinity, right? So splice, right? So basically, this is the space of piecewise linear function, right? So this is the space of piecewise linear function. And right, so this is the space of piecewise linear functions. All right, so splice function are also C infinity. So this is not good. Delta function function and not C0 continuous, right? So basically what you have is a space of piecewise linear functions. Delta function are not continuous, splice are not C infinity, and Lagrange functions are C infinity, right? So the only basis that we have is something like this. So you choose a function phi in all of those piecewise linear function, right? This function phi will be 0 at all other points except the point I, right? So I explain again. So phi belong to HH, and I is 1 n, and phi xj will be 1 if I is equal to j, 0 if I is different from j, right? So this is 0 and 1. Again, I'm going back to this example. You have x0, x1, x2, x3, x4. Suppose that I have only 5 points, right? So what is so then, because here I have 5 points, n will be n plus 1 will be 5, and then n will be 4, which means that I have 4 functions. I have phi1, phi2, phi3, phi4. So let me try to study those 4 functions, right? So what is phi1? Phi1 at 0 will be 0, of course, because of our condition, right? And phi1 at 1 will be 0. Now, what is phi1 at x1? So in this case, j is 1 and I is 1. So this is going to be 1, right? So I and j, they're both equal to 1, right? So which means that you have 0 here and you have 1 here. So you have 1. This is 1. All right, so this is 1 point. Now you have what? You have phi1 of h2. This is also, so what is the value of phi1 of h2? Right, I explain again. I define the function phi to be 1 to n. So in this case, n is 4, right? So according to Abdullah, Stephen, and Elisa, this is 0, right? Because I is equal to 1 and j is equal to 2, right? So this is Stephen and Elisa, right? So basically what I have is the following. So I have a function phi which belongs to this space of piecewise continuous function. Then I define phi of xi xj to be 1 if I is equal to j. So when so in this case n is 4, so I have 4 functions. Let us consider the first one. The first one have I and j that are both 1. So phi1 of x1 will be 1, and phi1 of x2 will be 0, because in this case I is 1 and j is 2, right? So here I'm gonna put 0, right? Now I'm gonna have phi1 of x3. This is also 0 because I is 1 and j is 3. So here I put a 0 here, right? So phi1 of x4 will be 0. So which means that here I have I is 1 and j is 4, right? So 1 and 4, they're different. So this should be 0. And of course, here you have 0, right? So what is the function that I have? I just have to connect all of the points. Right, so this is basically the function phi1. This is phi1, right? So I explain again. This phi1 function will be 0 at x2 It will be 0 as x3, should be 0 as x4. It is 0 at x0 and x5 because it belongs to h01. The only point that is not that is not a 0 is x1, and this is a piecewise linear and continuous function. So what I have to do is just to connect all of the points. So this is a head function. Now I'm gonna do phi2 so that you understand better what is the form of phi2. Right, so you have 0, x0, and this is x1, this is x2, this is x3, this is x4, and this is x5. Right, so then I have phi2 at 0 will be 0, and phi2 as 1 will be 0. So this is 0, and this is 1. So those things are 0. So what is phi2 as x1?
0.
What is 0? Yes, Molly got it. So Molly got it. So 1 is not correct, right, Steven? This is 0 because in this case J is 1 and I is 2. J is different from I, so this is 0. Right. So what is the point phi2 of x2? 1. Right. At least I got it. So this is 1. Right. So this is 1 according to Elisa. Right. So because here J is 2 and I is 2, they're equal. So basically this is 1. Now again, if you continue, it's gonna be like this. 0 and phi2 of x4 will be 0. So now because this is piecewise linear, so what you have to do is you connect all of the points, and you get a head function, right? So this is phi2. This is a head function as well. All right. So basically, this is the function phi2. Now the phi3 will be exactly the same, except that the head will be at the point 3. x3, x4, and this is x5. So phi3. So from this argument, you will see that okay, for phi3, it's gonna be like this. phi3, and the top will be the top of this hash will be at x3, right? So phi2, the top of this guy will be at x2 of this head, right? And at x2, and this is a head function at x3, right? And this is x0, x1, x2, x3, x4, and this is the last function. This is phi4. So this is a head function at x4, right? Right. So basically, you have a basis for this piecewise linear function space, and this basis will be those head function of this form, right? So this is the basis that we construct. So your homework will be show that this is a basis for HS, right? So your homework will be to show that this is a basis for HS. Basically, this is not difficult because you have a, I mean, you just write our definition and you get it. So this is our last homework. So is it clear? So basically, the basis for this HS will be all of the head function. So in a conclusion, the basis for HS will be the set of n hat function pi that we construct right, that we constructed before, right? So and this is also our homework, our last homework of this class, right? So then, so since phi1 phi n is a basis for VH, any function V in VH can be written as Vx is equal to the sum when n is going from 1 to n I Vi Vix, right? So so basically since this set of n hat functions form a basis for the space of piecewise linear functions VH, whose boundary at 0 is 0 and the boundary at 1 is also 0. So any function v in VH can be written as under this form, right? So you have Vx is going to be the sum of V1 V1 plus V2 V2 plus Vn Vn. So all of those Vi are real numbers. Any questions? Right. So now the problem B of UH V is equal to L. V becomes right. So in this case, because V can be written under this form, so how can I derive LV? Suppose that V is written under this form. What is the form of LV? So I go one step further. I have this is V1 plus V2 V2. Sorry. No, sorry. So this is a little bit too early. So now suppose that I have this problem and I have UH. So because all of the V in H can be written under this form, so UH can also, since UH is also in VH, we can write UH under the sum of C1 V1 of X plus C2 V2 of X plus Cn Vn of X, right? To find UH, we only need to find C1 Cn, since V1 and Vn are given. All right. So yes, thank you, Abdullah. So this is HS. I keep confusing between VH and HS, right? So thank you. So again, so this is HS, not VH. So again, any so as we explained before, this space is a basis for HS, right? Then any function v in HS can be written under the form of Vx is equal to the sum of V1 V1 plus V2 V2 plus Vn Vn, right? Now you want to solve this problem, which is the variational form on the finite dimensional space HH. So I write UH on the basis. So UH will be C1 V1 plus C2 V2 plus Cn Pn. Now to find UH, we only need to find all of the coefficients C1, C2, Cn, right? And in the next class, we're gonna study how to solve for C1 and Cn, and also the error analysis. Any questions? It's clear. So if there's no questions, we can stop our lecture here and see you next week. Have a nice weekend.
Thank you. Have a good weekend.
Thank you.
Nice
Bye.
weekend.
Bye. Thank you.
Thank you. Bye bye.
Thank you. Bye.